it's great to give a talk for SONET uh, because I prepared it especially. I put together some of the things I have been involved in the past many years, working on a topic like this. And since I don't see you while talking, what I suggest is that you interrupt me if you need any clarification at any time. Okay. And today I'm going to be talking about this what the title, from exploration strategy to construction materials. This is a very broad topic. We're going to be talking about many different things. Some are dealt with in a more technical way. Some others maybe in a not so deep fashion. But I hope that at least the message or some of the message is clear. Well, first, sustainable development. We have been talking about that, and for me, I generally, when I think of lunar exploration and planetary exploration and development, I think of sustainability in the terms that were stated by the United Nations in 1987. Some development, if you want, or some activity that meets the needs of the present generation without compromising the ability of future generations to meet their own needs. Here in this forum, we have talked several times about this topic. And also, I'm going to be addressing this issue that is going to be as a concept behind every single topic that I talk about. And I'm going to focus on these on three of these five topics that are usually dealt with when we talk about the design architecture, mission design architecture, what some people used to call before reference mission scenarios. Okay, so I'm going to be talking about environmental conditions, about consumables and materials, about construction, and energy and life support. I'm not an expert on life support. I could say very little about it. And energy, maybe we can later on we can organize another seminar on this because this is a very exciting topic as well. Um, so as far as environmental conditions, how do we summarize environmental conditions on the moon that we have to take into account? And remember that in principle, we want to keep as much as possible these environmental conditions, because one of the reasons why we will eventually be going to the moon to stay is because it offers us a quite drastically different environment that we can use for many things. It poses some problems as well. And then things that we have to think about, like the ultra high vacuum, like the thermal cycling. From day to night, temperatures can oscillate more than 150 degrees. The radiation environment, the micrometeorite impacts, dust, and probably many others, but these are some of the ones that I at least have direct reference on. Okay, about the lunar vacuum, someone said many years ago, someone said that the best way to get the best vacuum we can get on Earth is to bring a box to the moon, open it, close it, and bring it back. Okay, this is a very, very hard vacuum. In fact, some people talk about the lunar exosphere, and the lunar exosphere is no more than some volatilization of some elements due to cosmic and solar radiation on the surface. But this is a very, very rarefied gas, and so we have to keep in mind that if we are planning on activities on the surface of the moon, maybe this great asset that now is having the best vacuum we can think of might be compromised. Here, this is a work done by Geoff Landis about almost 30 years ago now, unbelievable, and where he put some numbers and he identified some of the activities that maybe are quite common in what we think might be lunar development and that will pose compromise on the vacuum. Like for a 20-person base or a 250-person industrial facility, there might be leakages from habitats, there are losses from airlocks, there's propellant, of course, and then as things go larger, we have to worry about how oxygen production that we're going to be talking some about today might affect that. Eventually, mining of helium-3, I don't know if that's very feasible or not, but also propellant and leakage from habitats. So lunar vacuum, I think, from a sustainable development point of view, has to be considered a priori at least like a great resource. And that has to be kept in mind that any activity that we do on the surface of the moon is affecting this lunar vacuum. So we have to at least be aware of what we're doing in this sense. Also, we have to worry about thermal cycles. On the moon, on the lunar day, it's very hot, and the lunar night is very cold. Okay, if we go to the equator, the average temperature is. These are, for those of you who do not have a technical expertise, this is degrees Kelvin. And this is so 0 degrees Kelvin would be minus 273. And if this would be 273 degrees, that would be 0 degrees centigrade, okay? So here we're looking at about minus 20. The average temperature in the moon, and the equator, is minus 20, but it has oscillations from day to night in 1 month. One day on the moon lasts for about 14 days, and one night for another 14 days. It can oscillate as much as almost 150 degrees. So those oscillations are different depending on where you go. You go to polar areas, for example, the average temperature is lower, but the oscillations are not so great. If you go to mid-latitudes, it's something in between. And of course, there are craters, especially in the lunar poles, that are so deep that the sunlight never reaches the bottom of the crater. And the average temperature is it's minus 230 degrees almost. So it's very, very cold. And of course, because there's no light there, there's no variation of the temperature. So one thing that we can do to try and avoid or minimize the effect that these thermal cycles might have on the materials, for example, this is something that's called thermal fatigue. The easiest solution could be to cover whatever we want to work on with a regolith. Regolith is a lunar soil, okay? Here, some years ago, we made some estimate on how different thicknesses of regolith cover could affect at different latitudes this oscillation. And because this eventually might also be a criterion that we will have to use to decide where we want to go, for what we want to go, okay? You see that if we go to the equator, that in principle could be advantageous for many other things. We would have to put over 2 meters of regolith just to get an oscillation of almost 3 degrees, okay? Which could be reasonable. People say in hospital standards, they talk about maximum oscillations of 2 degrees are okay. And I guess that we can go a bit beyond. If in this case, we can go to 3. Maybe 4 would be already too much, and 7 degrees oscillation would definitely be too much, and that requires 1.5 meters of cover with regolith. Okay. So we also have to worry about radiation. And a student of mine some years ago did a thesis where he studied this whole problem and did an assessment on the radiation hazards on the surface of the moon, and also the implications for human missions in the solar system. And radiation, of course, we have radiation from the sun, and we have radiation from the galaxy, what we call the galactic cosmic rays. And there are many particles that arrive on the surface of the moon, and here we have considered maybe those which are more massive and therefore might pose a greater danger for radiation dose. We have protons and neutrons, and the interesting thing that we have to take into account is that we have both inward radiation, that is to say the radiation that arrives on the surface from the outside, but also we do have backscatter radiation. Why? because this radiation impacting the surface of the moon is very, very energetic. So energetic that it's able to split some of the atoms from the soil, and those atoms and those particles will eventually go out again, and that would be an internal radiation source. So we might have the fact that we have some kind of shelter doesn't mean that we are 100% covered from radiation, especially the radiation coming from the interior. There are ways of designing shields, but that is a major issue. And you see that the energies of these are very, very high. We're talking about the mega electron volt, well, in fact, the giga electron volt, because there are thousands of mega electron volts in any case. You know, we'll see that the pattern of the incoming radiation from the outside is different as that radiation which is backscattered, and we can expect, of course, different fluence, that is different numbers of particles, integrated numbers of particles, depending on how much shielding we put. If we put 10 centimeters, we would cover to this level. 50 centimeters, we would be more covered. 1 meter, and then for backscatter, they are more similar. And this, among other things, allows us to optimize which is going to be the best way to cover to shield our habitats or surface modules or whatever from these both incoming and backscattered radiation. Okay, there are also solar particle events. You know, had the astronauts suffered one of these solar particle events, which are called also solar flares, they would not have never come back to the Earth. You know, they would have died because the radiation dose they would have gotten would be very, very high, lethal radiation. And those happen once in a while. They're pretty stochastic. I mean, we don't really know when one of these is going to happen. The warning we can send is about 8 minutes. The extravehicular activities, that is to say the astronauts, in the case one of these things happens, I mean, we'll have just a few minutes to get under shielding. Otherwise, they're going to be in serious trouble. Okay. So again, you see, these are for different solar particle events that have been recorded from 1956 until 2003. This is the WC model. It's not the water closet model, but it is the worst case scenario model. Okay. And this is the one that we use essentially to calculate which is the effective dose that is received by the people, you know, as a function of the shield that we do with the regoliths. Here we have two horizontal lines, and this is interesting because these are for female astronauts and these are for male astronauts. You see that the female astronauts are much more susceptible to suffer some kind of damage because of radiation than male astronauts. I will not be going into detail why that happens, but in principle, these are the safety and the safety factors that have to be considered as far as radiation is concerned. Okay. So look, for example, the age at exposure, if for a 25-year-old female, it's 0.4, 0.7, for a 35.6, 1, 0.915, 1.73. You see, and this is you know, this is based on a risk evaluation of developing a fatal cancer. Okay, and again, we can think this time about what is the shielding that we can put in the habitats to do that, and we evaluated different kinds of shielding, and we got very interesting results because the conventional shielding, the aluminum, that could be the structure of the spacecraft, is the worst. Okay, why? Because aluminum, being a metal, you know, it eventually can be a nucleus for producing additional radiation because the external particles impact aluminum, and aluminum, being a metal, emits, you know, acts as an emitter of new radiation. Then we have to go to light materials. Lithium hydroxide is used, for example, in the space station as a sink for CO2 because it forms lithium carbonate. and then it can be thermally treated and then decomposed again. The CO2 can be taken care of, and we have again the lithium hydroxide. So if we are going to be using something like that on the, there are other technologies as well for getting the CO2. But if we're going to be using this, I mean, it would be also good to have it evaluated. Keep in mind that this dose is the logarithmic scale. So just a little jump, we're talking about factors of 2 or 3, which are very relevant. The interesting thing is that water has the strongest, it's the most um, adequate or the best material to minimize this radiation, but also polyethylene. Polyethylene, this is light polyethylene, so that you have an idea what polyethylene is. It's a plastic. It's a supermarket bag, okay? These are made of light polyethylene. So you see the polyethylene and water have about the same capacity to shield, for this radiation on the surface of the moon. And that opens many possibilities because, as you know, water is going to be difficult to get there and not impossible. Eventually, it will have to be produced. But in any case, it will always be better to, it opens the possibility that polyethylene material can be transported from Earth. Polyethylene is very light, and it's much easier to bring there than water. Okay, these are strategies that can be discussed not only by engineers but also by politicians for a variety of reasons. But this is what also micrometeorite impacts. Okay, this is not an alarm. Okay, but we have to keep in mind that the lunar and the moon does not have an atmosphere. And every single shooting star that we see here on the Earth, means that a small particle has entered the atmosphere of the Earth's atmosphere, and has burned up there. It will not burn on the moon. The flux of the moon and the Earth is approximately the same because we are approximately in the same neighborhood. But these particles are hypervelocity. In many cases, they're hypervelocity particles. That means that they travel at speeds of kilometers per second sometime. Okay, so even small, they can do damage. Look, this is a crater formed by a micrometeorite. This is almost 1 millimeter in diameter. Okay, and on an Apollo sample. So one of these rocks that was collected by the Apollo astronauts when it was brought back to Earth. They looked at it in detail, and they saw, among many other things, they saw things like that. So even maybe more concerned we have to be about this one. This is an impact of a micrometeorite on a window of the space shuttle. This is a window of a space shuttle, specifically STS-35. So this is something that we have to take into account. There are technologies, there are multi-layer shields that eventually can be used for this, but well, this is a concern that this is something we have to take into account. Okay, and this graph was elaborated by Vanzani, and this shows more or less how many grams of micrometeorites we get as a function of per square meter. For example, if we go for 10 square meters, in 1 year we will get about 10 to the minus 7 grams of that. Okay, well, I don't know if this is too complicated to interpret, but this tells us, this is statistical, of course, gives us an idea on how many meteorites we can expect by square meter. Of course, as things grow larger and we introduce fragile materials, this has to be taken into account. And in fact, even on the helmet, on the glass cover of the helmet of the astronauts, of the Apollo astronauts, they identified a little tiny crack caused by a micrometeorite, and that impacted that helmet in just a few hours of extravehicular activity. Many of you have heard me talk about the dangers of dust, not so much about the danger, but that's something we have to be alert. The moon is a very dusty place. Okay, keep in mind that we don't have an atmosphere. This is very fine-grained that we have at the surface. It's heavily charged because the solar radiation, and when we lift it up, it takes a long time to settle down again. A long time means hundreds of years. For example, this is a picture from a video of one of the liftoffs of the Apollo module. You will see that there's plenty of stuff, there's really stuff, and a lot of dust being ejected at that time. There have been calculations that this dust will be kind of levitating on the surface of the moon before it settles down again on the surface for about 200 years. So this seriously compromises the activities that we might want to use the moon for. Also, maybe you have seen this picture. The moon is a dusty place. This is the suit of one of the astronauts, and this astronaut just walked around the moon. And you see that, from the feet until the knees or so, or the hip, it's almost totally covered with dust. Okay, imagine that you're finishing your extravehicular activity outside the habitat. You're going back, and of course, you have to change and get rid of this. Where do you keep this? I mean, how are you going to prevent these suits from being contaminated with dust? This is very fine grained. The finest grain is just a few microns, and this is heavily charged. This poses a serious concern. This is not going to go with an air current. This poses a serious, I would say, danger, for example, for any pressurized system, because this can get very easily on pressure valves, etc., and then cause malfunctions. So this is something we have to worry about too. Okay. Energy. About the energy, I told you this is. I'm not going to go into detail, but of course we have to define the energy requirements, and this requires to do a very accurate scalability study. Okay. And then the main sources of energy on the moon are solar resources and nuclear resources. Maybe others that are not maybe so direct to understand. And in any case, we will have to do a study on the feasibility of solar resource depending on the requirements, the advantage and disadvantage of each one, and how the use of one or other or both energy resources affects the site selection, because this is going to be an issue as well. As you will see in a few minutes, and we can eventually think that this is going to be controlled by the chemistry of the lunar soil as well. Okay, let's talk a bit about construction. Of course, when we talk about construction, we have to think architectural concepts first. Nothing as sophisticated at this point, at least, as the work that Alfredo and Owen and their colleagues prepare for the NUA concept. Okay, but I want to emphasize a couple of aspects. I will talk in a minute. Then, of course, we have to think about the building materials. How are we going to build things there? We have to think that the moon is a different planet and has different environmental conditions, and there are structural and service constraints that have to do with gravity, of course, whether we want to do things on the surface or underground. We have to always think about the radiation shielding. We have to think also about durability issues. Here, when we talk about construction materials, we have to worry about whether they dissolve and they are affected by salts or whatever. What are the durability issues that we have to worry about with construction materials on the surface of the moon? And there are some construction materials that may be used for habitats, and others for service modules or science infrastructures, depending on what we want to do. Okay, there are many possibilities. And as I tell you, from a structural point of view, what we know is that if we have some kind of, let's put a module or a habitat or a structure, this is 6 meters in radius, 12 meters in diameter. We know that for module this size, this will have to be covered with at least 5 meters of regolith. Okay. And then, of course, there is a slump stabilization slope, which for the moon, this is very difficult to calculate because of the charging. It can be estimated to be on the order of 36 degrees. So anything that, this is the dimensioning study, anything that has to be on the surface, and that if we think of regolith as the main shielding material, we'll have to have these kind of numbers, okay? We're talking about a structure that's 14 meters in height, okay? And 38 meters, almost 40 meters in width. It's not bad. So we took a detail of this, and for example, if this is a habitat, we take these 6 meters, okay, and we can make 2 floors there, the habitable area and the habitable area in the upper and lower floors. And here we can have, this was designed for a cast basalt, that is to say, we melt a rock and use, and when it solidifies, we give it the shape that we want. The minimum width of this, in addition to the shielding we have on top of that, in order for that to be a structurally, to work from a structural point of view, would have to be 1.5 centimeters. Okay, this poses additional constraints also on the kind of service that we can do that, and how good or bad it will resist the thermal cycling that we know is going to happen, at least on the upper parts of this structure. Okay. Let's talk about some materials. We could talk about many things, but I want to emphasize sulfur concrete because I had a chance to work on that. And why sulfur concrete on the surface of the moon? Because it has the strengths and the general properties are sometimes even better than those of conventional Portland cement concrete. Okay, in fact, sulfur concrete is used very heavily in cold environments, like in Canada. I mean, there are many companies in Canada that make a living, a very good living, by the way, of making sulfur concrete for a variety of applications. One thing that's very advantageous on the moon is that it doesn't need to hydrate. We don't need to mix it with water, of course. We just need to melt it at moderate temperatures, and then it sets very rapidly. It solidifies very rapidly. And in less than 24 hours, we have almost the maximum strength we can achieve with that material. And also that it can be placed at below freezing temperatures, something that that's the main reason why this material is used in countries like Canada, is because many times they have to put something with a structural capacity, and it's freezing, and concrete needs water, and then either you warm up the water or you use some other material. Sulfur concrete is a good choice for that. We did some study of sulfur concrete, and for that we used a lunar simulant. That is to say, we made the concrete instead. Instead of using terrestrial aggregates, we used this because we had some idea that the fine-grained nature of this simulant, which is very similar to the lunar regolith, will give some advantages on the mechanical behavior. I'm not going to go into detail now, but these are the numbers that we got. For different amounts of sulfur. They were heated, I think the temperature we had to go to, it was 165 degrees. So, we got compressive strengths between, this is just sulfur, okay? This is 100% sulfur, pure sulfur. This is very little compared to the others, but when we mix with the lunar simulant, we get to compressive strengths of almost 55 megapascals, which is very, very, very good, and in comparison to conventional Portland cement. Okay. So there have been some studies also on how much it costs. Forget about water now, and let's imagine that we are comparing Portland cement concrete with sulfur concrete. Portland cement concrete, we will require for these kind of things, we will have to use aggregates, the production of the binder, either cement or sulfur, water production. It's not the case for sulfur concrete. We'll have to mix the thing and to give the shape that we're interested on, and we can establish which products we want to make out of them. Okay. So, in summary, here the production of sulfur concrete is about 100 times more expensive than that of concrete, Portland cement concrete. Look, remember that Portland cement concrete is the cheapest material after water, okay? Because we use it in such a huge quantity. You know, in the Western world, each of us are consuming about 2.7 tons of concrete every year. You know, each of us is consuming that. You know, it's 1 cubic meter of concrete, of cement concrete, every year. This is a lot. Okay, of course, sulfur concrete is much more expensive. But then, if we go to some study that some authors did a few years ago, or some years ago, look, we're going to put these things on the surface of the moon and take into account a variety of costs, among others, transportation costs. Then we go that for a similar material, we can get 30 megapascals for the Portland cement concrete, 34 megapascals for sulfur concrete. You know, I told you that it's for some properties, for the strength, is even better. And you see that for two different conditions, you know, depending on the transportation costs, the prices are now almost the same. In fact, if the transportation costs are considered to be 6.7 times 10 to the $7 per ton, sulfur concrete becomes competitive as far as price is concerned. Okay, so this opens a possibility. Of course, I'm not saying that this is the choice that we have to do. Among other things, because there is a problem that has to be addressed, is that is there a lot of sulfur on the moon? And the answer, I tell you, is no. Okay? From a materials point of view, the research is done. It was kind of fun to demonstrate that when you mix it with something that looks very much like a lunar regolith, you can get this strength, these very competitive properties. But the fact is that there's no sulfur on the moon because the moon is depleted in volatile materials, and sulfur is quite volatile. Okay, so how do we know that? We have to go to exploration issues, and the exploration. I recognize I have a bias, but I think it will take a long time before the efficiency and completeness of an exploration activity can be done by a robot and a human at the same level. Humans continue to be, you know, much more efficient for these kind of things, and so this is my first choice. And also, we have to take into account that choices have to be taken, you know, as time goes as well. And look, I mean, this is one of the pictures I show to convince people that we really got there. I mean, that we humans got there. Picture on the left and picture on the right, and I say, well, there's a big difference on that. Find it, and then people find the print, the print here. Okay, this is this is the step of one of the astronauts. In fact, a piece of that rock was brought, you know, here. Here it's broken, and this was brought back to Earth. Okay, here it is. This is the piece that comes from there. Okay, and then we look at rocks like that under the microscope, and they show very nice colors that geologists use them, among other things, to identify what kind of minerals we have and to anticipate the properties and the chemical composition even before doing the chemical analysis. Okay, that's interesting because we do have samples from the moon, and we can do chemical analysis, And we see that they are quite similar to those, to many of the rocks that we have on Earth. For example, we have silicon here, titanium. There are some rocks that contain a lot of titanium. For example, these Apollo 11 rocks. Okay, uh, and the average titanium on the Earth is about 5 to 6 times lower than that. There are rocks that contain a lot of aluminum with respect to the others. It's almost 30%, and these other 10s, 15s. So aluminum could be interesting also. Um, well, there are. I mean, I don't think you see there potassium. These are the main things I want to emphasize now. Also, these rocks contain glass, natural glass, and this is a very interesting material from the construction point of view because it's quite reactive, and it can be used, for example, with some alkali solutions to make construction materials as well. Here, look at some of the samples. Apollo 15 and Apollo 17 are essentially pure glass. In fact, this sample, 74220, that's from the Apollo 17, was discovered by Jack Schmidt, who is a geologist, and he stepped on that, and then he realized that the rock was different. Probably a non-geologist would not have identified that at that point. And he collected the sample, and it turned out to be a beautiful, what is called a beautiful orange glass, that may be, in fact, very abundant in the immediate few centimeters below many parts of the regolith. Okay. In addition to surface exploration, of course, we can do orbital exploration. This is the most conventional, or at least the most common. I'm going to be talking about two missions. One of them to the moon, because I was involved in that. It was called the Smart One back in 2003. And this is the trajectory of a Smart One. And I tell you, this is kind of fun because it took us Europeans, I would say, 14 months to get to the moon, And the Americans made fun of us. Well, they were just kidding, of course, saying, "Hey, we made it in 3 years, and it's taking you 14 months." Well, the main reason is because the main objective for the development Smart One was the testing of the ionic thruster, in preparation for missions like missions to Mercury, etc., etc. Okay, and this is why maneuvering, in fact, was the main objective to control how easy or difficult was to maneuver that spacecraft was the main objective of the mission. But we took advantage of that and we put some instruments, what we call payload, okay? And these are the instruments that were set on the surface of this kind of box. This is the ionic engine, okay? And one of them, I was involved. It was a British instrument developed at Rutherford Appleton Laboratories near Oxford in the UK. And the PI was Manuel Grande. Manuel didn't speak a word of Spanish, but he was of the Spanish accent. That's the reason for his name. And this was DKIX. This was a CCD, okay? That word was sensitive to X-rays, okay? And collected X-rays emitted from the surface of the moon. And we know that those X-rays have characteristic wavelengths that tell us about the composition, among other things. Okay, with X-ray imaging, you can do things like that. Look, this is titanium, okay, which might be a strategic element on the surface of the moon, and we see that there are places where there's quite a high concentration of titanium. And this is very interesting from an exploitation point of view, for example, for the production of oxygen. We will see later on. Then the other mission I had to talk about was NASA's Lunar Prospector from 1998. This was a wonderful mission, I would say. It brought two of my favorite instruments ever flown on a spacecraft, which are the neutron spectrometer and the gamma ray spectrometer. They were developed at Los Alamos National Laboratories at New Mexico, the US. And look, what we do with these spectrometers is what we put them on the spacecraft, we look at the moon from an orbit, and we detect the particles that are coming out. coming out from the surface of the moon. When a cosmic ray, very energetic, gets in, as I told you before, it can split some of the atoms, and this is splitting. Some fast neutrons are produced, some thermal and epithermal neutrons. This is a nomenclature that tells us that the speed of these neutrons, or the energy of these neutrons, is lower than that of fast neutrons. Then it can generate secondary reactions, produce gamma rays, etc., etc. And also, there's some natural radioactivity that can be measured. For example, thorium. Thorium is a radioactive element from which we can do a nuclear reactor eventually, if we want, and there is enough, of course. Here, when we do that on the whole surface of the moon, we can get the actual concentrations of thorium, and we see that there are areas which are quite enriched in this material. I'm not saying that the concentration of thorium in these areas is high enough to go there immediately and exploit it as a resource, okay? But this is telling us that that some interesting locations, when we go into more detail, can be found there, okay? So this is a very, very important discovery, I think, that was done by the people at Los Alamos, and my favorite, because it turned out to be probably one of the most, in my opinion, one of the most important discoveries in the history of planetary science, was the following. It was because of this guy, because of the neutron spectrometer. When we look at the emission of neutrons from the surface of the moon, then we see something like that, higher concentrations with hotter colors, okay? But when we do a more detailed study and split this in 2-degree bands, we see the following. There are 2 locations where the emission of neutrons is significantly lower, okay? So you see the emission here, epithermal neutrons, for example, it's around 490 here, and then whoop, it drops. And this is very significant, and this is way beyond the error of the measurement. This happened to be at the North and the South Pole, So why that? What is happening there that caused this depletion in the neutrons emitted from the surface? Well, this is the idea. There's only one thing that is reasonable to think about that can cause this behavior, and this is the presence of hydrogen. Okay? Hydrogen, I mean, we said before that the moon was depleted in volatile elements. So why is hydrogen there? Hydrogen is, in fact, the most volatile element. Okay, there are 2 possibilities. One thing is that it has been implanted by the solar wind, okay, because it brings hydrogen from the sun to the moon. Very little, but that's a possibility. The other thing is that the hydrogen has somehow come there and accumulated from, let's say, water of cometary origin or whatever. We really don't know, and there are many hypotheses on that. We probably have to go there and get a sample and do some isotope analysis to see what's going on. But we have been able now to make a measurement. The amount of hydrogen is in the part per million, But this is, I would say, almost evidence that there is water, okay? The easiest way to produce these even small amounts of hydrogen on the surface of the moon is that we have frozen, of course, water there. 50 years ago, nobody would have even thought that water could be present on the moon. Now we know that it's the case. And in fact, this thing has been verified by reanalyzing some data from other spacecrafts that went by, for example, Galileo. Okay, I think even every time I talk about that, I get excited because I tell you, I think this is one of the most important experiments of the history of planetary science. And we have it here, just less than 400,000 kilometers from here. We can eventually go there. We think of resources. If we want to say, well, probably this is the first thing that we have to do is produce hydrogen, either for fuel or for life support systems or for whatever. Airbus, in fact, is advertising that they have a system to produce hydrogen already. So far, this is the most sophisticated science that they do. It's just showing the picture. But where is oxygen on the moon? Here on the Earth, it's very easy to get oxygen because 20% of the atmosphere is made of oxygen. But on the moon, oxygen is trapped in rocks. It's trapped in a molecule that forms most rocks there. It's called silicates. Okay? Silicate is a molecule that has one atom of silicon and four atoms of oxygen. Okay? This is called the silica tetrahedron. These tetrahedrons, which are the basic blocks of minerals, can get in very complicated arrangements, three-dimensional arrangements that eventually form rocks. Okay, imagine now that we take all the oxygen, okay, from a rock like this one and put it in this kind of container. You know, this is 8 liters. Okay, so it's about 2 something gallons. Okay, 2.5 gallons or so of oxygen. We fill it with oxygen. Okay, why we do that? Is this a game? Well, in that rock that weighs just 1.6 kilograms, with the oxygen of this rock, we can fill all these containers, water bottles. Okay, 8 liter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 80. You know, 11, 1, 2, 3, 4, 5, 6. 66 times 8 liters, okay, of oxygen. Okay, so there is a great potential to exploit oxygen if we know how to remove it from the rocks. There have been many approaches. There is a mineral called ilmenite that is composed of iron, titanium, and oxygen. It's quite easy to extract oxygen from there, but you know, we need some temperature that we could get with solar concentrators, and then split the molecule of ilmenite into iron. Then we get some metal that we can use for other things. Titanium, that can be, this is a semiconductor, if properly treated, can also give us some interesting catalytical, photocatalytical properties. And water. We can split that water with solar energy, you know, and use the hydrogen to reduce more ilmenite. And then this oxygen, we can produce up to 16 grams of oxygen per 150 grams of ilmenite, more or less. So about 10%. It's not great, you know, but there is a lot of titanium, and this titanium on the surface of the moon is most probably in the form of ilmenite, because this is what we see in the Apollo samples. So 10% is not great, but it's very, very promising. There have been last year, there's some British scientists have published the application of a method that can be used industrially, in fact, to handle industrial amounts of material to produce oxygen on the surface of the moon. They took, not regularly, they took a lunar simulant material, okay? They applied the metalysis is the name of the company. FCC these are the initials of the authors of this process. And in principle, they produce oxygen gas and powered metals. This is great news, you know. The not so good news is that they need to bring a lot of material. There is no calcium chloride on the surface of the moon. There is no tin dioxide on the surface of the moon. We have to bring some material with, okay, if that works, I mean, that should not be a big deal. And look, in 50 hours, they managed to remove, to get almost 32 or 33% of all the oxygen. So from the rocks, okay? So this is almost 3 times higher the efficiency as the ilmenite, you know, as far as the amount of oxygen is concerned. However, there are some observations that we all have to worry about, in the fact that the amount of remaining oxygen in the material that has been reduced just follows the opposite trend as it should. I will not go into detail, but this probably is indicating that this is due to some fast reoxidation on the terrestrial atmosphere, you know, because this was carried out in terrestrial laboratories, evidently. And this could not be a problem on the surface of the moon, but there are some data that had to be readdressed. And this is a very recent paper. It doesn't have a year yet. So you can choose your model. You want to go there, have to cover things with regolith, whatever shapes you want, and go there and make it happen. We are contributing very modestly to make it happen. And as I told some of you, currently we have 2 students working on their master's thesis at UPC. Carlos Ibanez, who's the next speaker here at the SONetTalks, by the way, will be talking about asteroidal volatiles for the development of planetary outposts in the case of the moon. That's an original approach. And Jack Wallis is working on the exploration and in situ resource utilization of lunar space weathering materials that has to do with the fact that we are reducing basaltic materials to get metal and use that metal to give some properties, some engineering properties to regolith materials that allow us to do 3D printing, for example, for construction. Thank you very much. I would not like to end before making some advertisement of my book that we published with Miquel Sureda. In fact, we acted as editors. This is a book that was authored by 10 students of a course of aerospace engineering in UPC in Terrassa 2 years ago. And we are very proud. And in fact, we even got a prize for the most downloaded book of this collection at UPC. Thank you very much. It was fun.